This is a video from section 11.2 in my Calculus 2 class. The summation from n equal 1 to infinity of AR to the n minus 1 is a geometric series. This series converges if the absolute value of r is less than 1 or r is greater than -1 and less than 1. This series diverges if the absolute value of r is greater than or equal to 1. If the series converges, then the summation from n equal 1 to infinity of AR to the n minus 1 is equal to A divided by 1 minus R. And so a quick note here, A doesn't equal 0. Also note, the summation from n equal 1 to infinity of AR to the n minus 1 is equal to the summation from n equals 0 to infinity of AR to the n. So notice how the lower limit went down 1 and the exponent on the r increased by 1 to counterbalance. Now, let's take a look at the first example. So we're going to determine whether or not the summation from n equal 1 to infinity of 3 to the n plus 1 times 4 to the negative n converges or diverges. But this can be written as the summation from n equal 1 to infinity of 3 times 3 to the n divided by 4 to the n. But this is equal to the summation from n equal 1 to infinity of 3 times 3/4 times 3/4 to the n minus 1. So notice the lower limit is 1. The exponent on the r, in this case where r is 3/4, is equal to n minus 1. Now, the absolute value of r is equal to 3/4, and that's less than 1. And so what that tells me is that this series converges by geometric series. Okay, now we need to find out the sum of the series. So let's backtrack a tiny bit. Now, A is 3 over 1 times 3 over 4, which is equal to 9/4. And then R is 3/4, right? Which is less than 1. So let's plug that in. The summation from n equal 1 to infinity of 3 to the n plus 1 times 4 to the negative n is A, which is 9/4, divided by 1 minus 3/4. Now, I want to get rid of the fraction, and so to do that, I'm going to multiply the numerator and denominator by 4. And so 9/4 times 4 is 9, and then 1 minus 3/4 is, times 4, by the way, is equal to 1. And so we get 9 over 1, and that's equal to 9. And that's how we do example 1. So let's take a look at example 2. Suppose we have the summation from k equal 1 to infinity of sine of 100 to the k power. So we need to write this as the summation from k equal 1 to infinity of sine of 100 times sine of 100 to the k minus 1. Now, the absolute value of r is sine of 100, which is less than 1. And so what that tells me is that this series converges. Now, A is sine of 100, and R is also sine of 100. So again, A is sine of 100, R is also sine of 100. And so, therefore, let's find the actual sum. So we're going to get the summation from k equal 1 to infinity of sine of 100 raised to the k power. So this is sine of 100, that's A, divided by 1 minus sine of 100. And so that's a over 1 minus r. And that's fine for that. So let's go to the next example. We'll call this example 3. And suppose we have the summation from n equal 1 to infinity of 1 divided by 1 plus 2/3 raised to the n power. Now, we're going to look at the limit as n goes to infinity of 1 over 1 plus 2/3 to the n. Now, as n gets large, right, 2/3 to the n goes to 0. And so this is 1 divided by 1 plus 0, which is equal to 1, which doesn't equal 0. And so by the test for divergence, the summation from n equal 1 to infinity of 1 over 1 plus 2/3 to the n diverges. You're done. There's really nothing you could do here. Here's another one. Let's take a look at example 4. Suppose we have the summation from n equal 1 to infinity of natural log of n squared plus 1 divided by 2n squared plus 1. And so I'm going to look at the limit as n goes to infinity of n squared plus 1 divided by 2n squared plus 1. And this is the limit as n goes to infinity of. In the numerator, I'm going to factor out an n squared. When I do that, I get 1 plus 1 over n squared. And then I'm going to factor out an n squared in the denominator, and when I do that, I get 2 plus 1 over n squared. So the n squareds cancel, and as n goes to infinity, 1 over n squared goes to 0. Okay? And so the final result here is 1/2. So I'm going to let f of x equal natural log of x. F is continuous. At 1/2. Therefore, the limit as n goes to infinity of natural log of n squared plus 1 divided by 2n squared plus 1 is natural log of the limit as n goes to infinity of, and I get n squared plus 1 divided by 2n squared plus 1. Now remember, as n gets big, n squared plus 1 over 2n squared plus 1 is going to 1/2. And so this is natural log of 1/2. That is absolutely not 0. And so therefore, the summation from n equal 1 to infinity of natural log of n squared plus 1 divided by 2n squared plus 1 diverges by the test for divergence. You're done. Now here's the deal. If this ended up being 0 for some reason, we don't know anything about that summation. We know nothing. So we have to be careful there. Yeah, so that's what's going on for that question. Let's take a look at example 5. Suppose I have the following. This could be pretty interesting. So suppose I had the summation from n equal 1 to infinity of natural log of n over n plus 1. But that's the summation from n equal 1 to infinity of natural log of n minus natural log of n plus 1, just like this. Now, this is pretty traditional. We're going to use the definition. So I'm going to let S sub k, that is, equal the following. So I'm going to get natural log of 1 minus natural log of 2 plus natural log of 2 minus natural log of 3 plus natural log of 3 minus natural log of 4 plus natural log of k minus natural log of k plus 1. Like so. All right, now, let's kind of look at this very carefully. The natural log of 2's cancel. The natural log of 3's cancel. Are we in agreement that the natural log of 4 will cancel that first term in the next? So, in other words, if I plug in n equal 4 here, I get natural log of 4 minus natural log of 5. And then natural log of k will cancel out the natural log of k that appears in the previous. In other words, when I replace n with k minus 1. So what ends up being left over is equal to. Now, natural log of 1 is 0. And then I'm going to go minus natural log of k plus 1. So, therefore, the limit as k goes to infinity of s sub k is the limit as k goes to infinity of negative natural log of k plus 1. But that's negative infinity. So, by definition, we know that S sub k, this sequence of partial sums, diverges, right? And so, therefore, the summation from n equal 1 to infinity of natural log of n over n plus 1 also diverges. And you're done. So that's a classic example of a telescoping sum. And that was example 5. And that's a good stopping point for this video. And this is a video on section 11.2, and we did 5 examples of a geometric series. Okay, all right, thank you.